How do we actually travel through the vast emptiness of space? It's not just about rockets and engines. It's about dancing with the fundamental forces of the universe itself. If you find comfort in these gentle explorations of science, I'd be grateful if you'd consider subscribing and liking this video. The visuals are here for you, but feel free to close your eyes, breathe deep, and let your imagination soar through the cosmic void. Also, I'd love to know where you're listening from tonight. Comment your time and location below. Imagine you're standing in your backyard on a clear night, looking up at the stars. You see that tiny dot of light that might be Mars, or perhaps the steady glow of the International Space Station passing overhead. And somewhere in that vast darkness, spacecraft are gliding silently through the void, carrying our hopes and dreams to distant worlds. But here's what makes this truly extraordinary. These machines aren't roaring through space like jets through the atmosphere. They're not constantly burning fuel like cars on a highway. Instead, they're following invisible pathways carved by gravity itself, surfing the curves of space-time in an elegant cosmic ballet that would make poets weep. Welcome to this journey through one of the most beautiful and counterintuitive aspects of modern science. Traveling through space isn't about fighting against the universe, but about learning to dance with it. We'll explore how a spacecraft can travel for years on just a few minutes of engine burn, how we can slingshot around planets to gain impossible speeds, and why the fastest way to reach some destinations is often the most curved path through the heavens. The story begins with something that might surprise you. Space isn't actually empty. It's not the void we often imagine, filled with nothing but darkness and cold. Instead, space is alive with invisible forces, curved by massive objects, flowing like an ocean of gravitational currents that stretch across billions of miles. Think of it this way. Imagine you're standing on a vast trampoline that stretches beyond the horizon. Now place a bowling ball in the center. The fabric curves around it, creating a depression. Roll a marble nearby, and it doesn't travel in a straight line. Instead, it follows the curves created by the bowling ball, spiraling around it in graceful arcs. This is exactly what's happening in space, but on an unimaginable scale. The sun is like that bowling ball, warping the fabric of space-time itself. The planets are like marbles, following the curves created by this cosmic depression. And when we launch a spacecraft, we're not just throwing it into empty space. We're placing it on this invisible trampoline of curved space-time, where it will naturally follow the paths carved by gravity. But here's where it gets truly magical. Once a spacecraft is moving through space, it wants to keep moving forever. There's no air resistance to slow it down, no friction to steal its momentum. This is Newton's first law in its purest form. An object in motion stays in motion unless acted upon by an external force. On Earth, we're so used to things slowing down. When you slide a book across a table, it comes to a stop. When you throw a ball, it eventually falls to the ground. But in space, there's nothing to stop that motion. A spacecraft traveling at thousands of miles per hour will continue at exactly that speed, in exactly that direction, for potentially millions of years, unless something changes its path. This creates a beautiful paradox. The hardest part of space travel isn't staying in motion. It's getting into motion in the first place, and then changing that motion when you need to. Every spacecraft launch is essentially a battle against Earth's gravity, a tremendous expenditure of energy to reach what we call escape velocity. But once you're free of Earth's gravitational embrace, the universe becomes your highway. And that highway has no speed limits and no friction. Now, you might think that traveling from Earth to Mars is simply a matter of pointing your spacecraft toward the red planet and flying straight there. After all, that's the shortest distance, right? But in space, the shortest distance is rarely the fastest path, and the fastest path is almost never a straight line. This is because everything in space is moving. Earth is orbiting the Sun at about 67,000 miles per hour. Mars is orbiting at about 54,000 miles per hour, but in a larger orbit. The Moon is orbiting Earth. Jupiter's moons are orbiting Jupiter. It's like trying to jump from one moving train to another, while both trains are on curved tracks that are themselves moving through a landscape that's spinning and tilting. Space missions aren't planned like road trips. They're planned like cosmic choreography, where timing is everything. Engineers don't just calculate where Mars is today. They calculate where Mars will be in 6 months, 9 months, a year from now. They plot not just a path through space, but a path through time. And this leads us to one of the most elegant aspects of spacecraft travel, the concept of transfer orbits. Instead of flying directly to our destination, spacecraft follow curved paths that take advantage of the natural motion of celestial bodies. The most famous of these is called a Hohmann transfer orbit, named after the German engineer Walter Hohmann, who first described it in 1925. You want to travel from Earth's orbit to Mars' orbit. Instead of flying straight across, you fire your engines just once to place your spacecraft on an elliptical path that intersects both orbits. At the point where you leave Earth's orbit, you're at the closest point to the Sun. At the point where you reach Mars's orbit, you're at the farthest point from the Sun. The beautiful thing about this elliptical path is that you're not fighting against the Sun's gravity, you're using it. When you're closer to the Sun, gravity pulls you faster. When you're farther away, you naturally slow down. It's like rolling a ball up and down hills, using the landscape itself to control your speed. But here's what makes this truly remarkable. Once you've fired your engines to enter this transfer orbit, you can essentially turn them off. For months, your spacecraft will coast through space, following this precise elliptical path carved by gravity alone. No fuel burned, no energy consumed, just the eternal dance of orbital mechanics carrying you toward your destination. This is why spacecraft can travel for years on relatively small amounts of fuel. The engines aren't running constantly like a car engine. Instead, they provide brief, powerful bursts at precisely calculated moments. A few minutes of engine burn can change a spacecraft's trajectory for months or even years. But sometimes, even the elegant efficiency of transfer orbits isn't enough. Sometimes we need to travel faster, farther, or with more payload than our rockets can directly provide. This is where one of the most ingenious techniques in all of space exploration comes into play: the gravity assist, also known as a gravitational slingshot. Imagine you're on a merry-go-round and someone throws a ball to you. As you catch the ball and then throw it back, you can add your rotational speed to the ball's velocity. The ball leaves your hand moving faster than when it arrived. Now, scale this up to planetary proportions. When a spacecraft approaches a moving planet, it falls into the planet's gravitational field, picking up speed as it gets closer. If the spacecraft's trajectory is carefully planned, it can whip around the planet and be flung out at a much higher velocity than it had when it arrived. The spacecraft steals a tiny bit of the planet's orbital energy, gaining speed without burning any additional fuel. This technique has enabled some of our most ambitious space missions. The Voyager spacecraft, launched in the 1970s, used gravitational assists from Jupiter and Saturn to reach speeds that would have been impossible with chemical rockets alone. They borrowed energy from these giant planets, accelerating to velocities that carried them to the outer reaches of our solar system and beyond. But gravity assists aren't just about speed. They're about possibility. They allow us to reach destinations that would otherwise be beyond our technological capability. They let us send heavier spacecraft, carry more scientific instruments, and explore regions of space that chemical propulsion alone could never reach. The planning required for these gravitational slingshots is mind-boggling. Engineers must calculate not just where the planets will be, but how their gravitational fields will interact with the spacecraft's trajectory. They're essentially playing three-dimensional billiards on a cosmic scale, where the table is constantly moving and the balls are planets weighing billions of tons. And sometimes the most efficient path involves multiple gravity assists. A spacecraft might swing by Venus, then Earth, then Jupiter, gaining speed with each encounter. These trajectories look like elaborate spirals when plotted on paper, but they represent the most fuel-efficient way to reach distant destinations. Consider the Cassini mission to Saturn. Instead of flying directly to the ringed planet, Cassini followed a 7-year trajectory that included gravity assists from Venus twice, Earth once, and Jupiter once. This complex path allowed the spacecraft to carry enough fuel and scientific instruments for a 13-year mission around Saturn, something that would have been impossible with a direct flight. But perhaps the most beautiful aspect of spacecraft travel is how it reveals the hidden connections between celestial bodies. Every planet, moon, and asteroid influences every other object through gravity. When we plan a space mission, we're not just calculating the path of one spacecraft. We're mapping the invisible web of gravitational relationships that connects everything in our solar system. This web extends far beyond what we can see. The gravitational influence of Jupiter affects the orbits of asteroids in the inner solar system. The moon's gravity influences not just Earth's tides, but also the trajectories of spacecraft passing nearby. Every celestial body is constantly tugging on every other body, creating a dynamic, ever-changing landscape of gravitational forces. And spacecraft navigate this landscape with exquisite precision. Mission controllers can predict where a spacecraft will be months or years in advance, accounting for the gravitational influences of multiple planets and moons. They can plan course corrections that will be executed years in the future when the spacecraft reaches a specific point in space where a small engine burn will produce exactly the desired change in trajectory. This level of precision seems almost magical, but it's based on the fundamental predictability of celestial mechanics. The same mathematical principles that allowed Newton to predict the return of Halley's Comet allow us to navigate spacecraft across billions of miles with stunning accuracy. Yet there's something even more profound happening when we consider how spacecraft actually move through this cosmic dance. You see, when we watch a rocket launch, we witness the most dramatic and energy-intensive part of the entire journey. Those massive engines, burning thousands of pounds of fuel per second, fighting against Earth's gravitational embrace with raw, thunderous power. But that spectacular display represents only the tiniest fraction of the spacecraft's actual journey. Think about this for a moment. The Space Shuttle's main engines burned for just 8.5 minutes during launch. Yet the missions lasted weeks. The Apollo spacecraft that carried astronauts to the moon used their main engines for mere minutes during the entire 3-day journey. The rest of the time, they were gliding silently through space, carried by momentum and guided by gravity. This reveals something beautiful about the nature of space travel. It's not about constant propulsion. It's about understanding timing, patience, and the art of celestial navigation. Once you escape Earth's atmosphere and reach orbital velocity, space becomes a realm where small, precise movements can create enormous changes over time. Consider the delicate process of orbital rendezvous. When a cargo spacecraft approaches the International Space Station, it's not simply flying straight toward it. Both vehicles are traveling at over 17,000 miles per hour, orbiting Earth every 90 minutes. The approaching spacecraft must match not just the station's position, but its velocity, its orbital plane, and its rotational orientation. It's like threading a needle, while both the needle and the thread are spinning on separate carousels. The technique used is counterintuitive. To catch up with something ahead of you in orbit, you don't speed up directly toward it. Instead, you slow down, dropping to a lower orbit where you naturally move faster, then raise your orbit again when you're in the right position. To move closer to Earth, you fire your engines backward. To move farther away, you fire them forward. In space, up is not always up, and forward is not always the fastest way ahead. This orbital ballet requires a fundamental shift in thinking. On Earth, if you want to go somewhere, you point yourself in that direction and apply force. In space, you must think in curves, ellipses, and spirals. You must plan not just where you want to go, but when you want to arrive. Because timing determines trajectory, and trajectory determines possibility. The mathematics behind these movements are elegant in their complexity. Every spacecraft carries computers that constantly calculate its position relative to Earth, the Moon, the Sun, and other celestial bodies. These calculations account for the gravitational influences of multiple objects simultaneously, creating what mathematicians call the n-body problem. For 2 objects, the equations are simple. For 3 objects, they become significantly more complex. For a spacecraft influenced by Earth, Moon, Sun, and planets, the calculations require some of the most sophisticated computers ever built. But here's what makes this truly remarkable. Despite this complexity, the underlying principles are based on laws of physics that were discovered centuries ago. Newton's laws of motion and universal gravitation, refined by Einstein's insights into space-time, provide the foundation for every spacecraft trajectory ever flown. We're using 300-year-old physics to navigate 21st century technology across distances that boggle the imagination. And yet, space travel is still full of surprises. Sometimes spacecraft encounter phenomena that their planners never anticipated. Solar winds can push lightweight spacecraft off course. The uneven distribution of mass within planets creates gravitational anomalies that subtly alter trajectories. Even the pressure of sunlight itself can affect a spacecraft's path over long distances. These effects are tiny, almost negligible. But over the vast scales of space and time, tiny effects accumulate into significant changes. A deviation of just a few feet per second can mean the difference between a successful mission and missing your target by thousands of miles. This is why mission controllers constantly monitor spacecraft trajectories and make small corrections along the way. These course corrections are themselves marvels of precision. A thruster firing that lasts just seconds can adjust a spacecraft's path by thousands of miles at its destination. The timing of these burns is critical. Fire too early, and you waste fuel making corrections later. Fire too late, and you might not have enough fuel to reach your target. Mission planners must balance these factors while accounting for the changing positions of planets, the degradation of spacecraft systems over time, and the finite fuel supply carried on board. The fuel itself tells a fascinating story. Unlike cars that can refuel at gas stations, spacecraft must carry every drop of fuel they'll ever use from the moment they launch. This creates a fundamental constraint on space missions. Every pound of scientific equipment means 1 less pound of fuel. Every pound of fuel means 1 less pound of scientific instruments or structural mass. This constraint has driven incredible innovation in spacecraft design. Engineers have developed ion drives that can operate for years on tiny amounts of fuel, providing gentle but continuous thrust. They've created solar sails that use the pressure of sunlight itself for propulsion, requiring no fuel at all. They've designed spacecraft that can hibernate for years between planetary encounters, conserving power and extending mission lifetimes. But perhaps the most ingenious innovation is the use of atmospheric braking, or aerobraking. When a spacecraft arrives at a planet with an atmosphere, it can use that atmosphere to slow down instead of burning fuel. The spacecraft dips into the upper atmosphere, using atmospheric friction to reduce its velocity. It's like using air resistance as a brake, but it requires exquisite precision. Dip too shallow, and you don't slow down enough. Dip too deep, and the spacecraft burns up like a meteor. Mars missions routinely use aerobraking to transition from high-speed interplanetary trajectories to stable orbits around the red planet. The spacecraft makes hundreds of passes through Mars' thin atmosphere, each pass removing a small amount of velocity. Over months, these tiny atmospheric touches gradually reshape the orbit from a highly elliptical path to a circular one suitable for scientific observations. This technique reveals something profound about space travel. Success often comes not from brute force, but from patience and precision. Instead of using powerful engines to slow down quickly, spacecraft can use the gentle touch of atmospheric molecules over hundreds of orbits. It's a perfect metaphor for how space travel works in general. Small forces, applied consistently over vast periods of time, can achieve remarkable results. The same principle applies to the most ambitious space missions. When we send spacecraft to the outer planets, we're not just overcoming distance, we're overcoming time. The journey to Jupiter takes years. The journey to Saturn takes even longer. By the time our spacecraft arrive, the teams that built them may have retired. The technology that seemed cutting edge at launch may be obsolete by arrival. This creates unique challenges for spacecraft design. These machines must be built to operate for decades in one of the harshest environments imaginable. They must survive temperature swings from hundreds of degrees above zero to hundreds of degrees below. They must function in perfect vacuum, bombarded by radiation, with no possibility of repair or maintenance. Yet somehow, they do. The Voyager spacecraft, launched when disco was popular, are still transmitting data from the edge of our solar system. They've operated for over 4 decades, far longer than their designers ever imagined possible. They've survived solar storms, equipment failures, and the gradual decay of their plutonium power sources. They continue to send back information about regions of space no human-made object has ever explored. This longevity is a testament not just to engineering excellence, but to the fundamental nature of space travel itself. Once a spacecraft is moving through space, it can continue moving almost indefinitely. There's nothing to wear out, nothing to corrode, nothing to clog or break down from use. The spacecraft becomes a permanent resident of the cosmos, a human artifact that will outlast our civilization. Consider the golden records aboard the Voyager spacecraft, containing sounds and images from Earth. These records will survive long after our planet is gone, drifting through interstellar space as monuments to human curiosity and ingenuity. In 1 billion years, when our sun has evolved beyond recognition, these spacecraft will still be journeying through the galaxy, carrying our message to the stars. This perspective transforms how we think about spacecraft travel. These aren't just machines going from point A to point B. They're humanity's first steps into the cosmic ocean, our initial attempts to become a spacefaring civilization. Every spacecraft we launch is an ambassador, representing our species in the vast darkness between worlds. And the techniques we've developed for spacecraft travel are teaching us about possibilities we've barely begun to explore. The same gravitational assists that send robotic probes to distant planets could one day accelerate human expeditions to Mars and beyond. The same orbital mechanics that position satellites around Earth could help us build permanent outposts throughout the solar system. But perhaps most importantly, spacecraft travel reveals the interconnectedness of everything in space. When we launch a mission to Jupiter, we're not just sending a probe to one planet. We're placing a new participant in the gravitational dance that includes every object in our solar system. That spacecraft becomes part of the cosmic choreography, its tiny mass contributing to the overall gravitational environment. This interconnectedness extends to the missions themselves. The data returned by one spacecraft informs the design of the next. The techniques proven on one mission enable the ambitions of future missions. Each successful journey through space adds to our collective knowledge of how to navigate the cosmic ocean. As you drift deeper into contemplation of these cosmic journeys, consider that you're witnessing the birth of a new chapter in human history. For millions of years, our species was confined to the surface of one small planet. But in the span of a single human lifetime, we've learned to send our creations across the solar system and beyond. We've touched the surface of Mars with robotic hands. We've tasted the methane lakes of Titan. We've felt the magnetic fields of Jupiter and heard the radio whispers of Saturn's rings. Through our spacecraft, we've experienced the solar system not as distant lights in the sky, but as real places with their own weather, geology, and stories to tell. And this is just the beginning. The techniques we're developing today will enable the missions of tomorrow. Solar sails could carry lightweight probes to nearby stars within a human lifetime. nuclear propulsion could slash travel times to the outer planets. Advanced ion drives could enable missions to hundreds of asteroids and comets. The gentle art of spacecraft travel is teaching us to think in cosmic terms, to plan for decades and centuries, to work with the fundamental forces of nature rather than against them. It's showing us that the universe isn't empty space punctuated by isolated objects, but a dynamic, interconnected system where everything influences everything else. In learning to navigate this system, we're not just developing technology, we're developing wisdom. We're learning patience, precision, and the art of thinking in multiple dimensions across vast scales of time and space. We're discovering that the most efficient path is often the most elegant one, and the most elegant solutions work with nature rather than against it. Tonight, as we continue our journey through the cosmic ocean, we encounter something that might surprise you. The most advanced spacecraft propulsion systems don't roar with flames like the rockets we see in movies. Instead, they whisper with the gentle touch of individual atoms, creating thrust so subtle you could barely feel it if you held the engine in your hand, yet so persistent that over months and years, they can accelerate spacecraft to incredible velocities. These are ion drives, and they represent a completely different philosophy of space travel. Instead of the explosive power of chemical rockets, ion drives use electricity to accelerate individual particles to extremely high speeds. Imagine holding a grain of sand and throwing it as hard as you can. Now imagine throwing 10,000 grains of sand one at a time, each moving 10 times faster than you could throw them by hand. The total effect over time becomes enormous, even though each individual particle carries very little momentum. The process is elegantly simple in concept. Electricity strips electrons from atoms of xenon gas, creating charged particles called ions. These ions are then accelerated through an electric field and expelled from the spacecraft at speeds of up to 60,000 miles per hour. The reaction pushes the spacecraft in the opposite direction, following Newton's third law of motion. But here's what makes ion propulsion truly remarkable. While a chemical rocket might burn for minutes and then fall silent, an ion drive can operate continuously for years. The thrust is so gentle that if an ion drive were sitting on your desk, you couldn't even feel it pushing. Yet over the course of a multi-year journey, this whisper-quiet engine can change a spacecraft's velocity by thousands of miles per hour. This creates possibilities that chemical propulsion simply cannot achieve. The Dawn spacecraft used ion propulsion to visit two different asteroids, Vesta and Ceres, something that would have been impossible with conventional rockets. The spacecraft essentially spiraled outward from one asteroid, then spiraled inward to the next, using its ion drive to gradually reshape its orbit over the course of years. But ion drives represent just one frontier in our evolving understanding of space propulsion. Engineers and scientists are exploring even more exotic possibilities. Solar sails use the gentle pressure of sunlight itself to propel spacecraft. These gossamer structures, thinner than human hair but covering areas larger than football fields, catch photons from the sun like sailboats catch wind. The pressure is incredibly subtle. Sunlight exerts about the same force on a solar sail as the weight of a paperclip would exert on your hand. But in the vacuum of space, with no friction to slow them down, spacecraft equipped with solar sails can gradually accelerate to remarkable speeds. The Japanese spacecraft Icaros successfully demonstrated solar sailing on its way to Venus, proving that spacecraft can literally sail on starlight. Even more intriguing are the theoretical possibilities that emerge when we consider the fundamental nature of spacetime itself. Scientists have proposed concepts like the Alcubierre drive, which wouldn't move a spacecraft through space at all, but would instead compress space in front of the craft and expand it behind, creating a bubble of warped spacetime that could theoretically travel faster than light without violating relativity. These ideas remain far beyond our current technology, but they illustrate how our understanding of space travel continues to evolve. Each breakthrough in physics opens new possibilities for propulsion, navigation, and exploration. What seems impossible today may become routine tomorrow. But even with our current technology, we're accomplishing things that would have seemed like magic to previous generations. Consider the precision required for some of our most delicate spacecraft maneuvers. When the Cassini spacecraft ended its mission at Saturn, mission controllers didn't just crash it into the planet. Instead, they carefully planned its final trajectory to ensure it would burn up in Saturn's atmosphere, protecting the potentially habitable moons from contamination. This final dive required navigating through the gap between Saturn and its rings, a region no spacecraft had ever explored. The gap is only about 1,500 miles wide, but Saturn and its rings are moving at different speeds, creating a dynamic environment where the safe passage changes moment by moment. It was like threading a needle while riding a roller coaster. But the Cassini team executed it flawlessly. These kinds of precision maneuvers reveal something profound about how we've learned to think about space travel. We're not just throwing objects into space and hoping they arrive at their destinations. We're conducting symphonies of orbital mechanics, choreographing the movements of spacecraft across vast distances with mathematical precision that would have been incomprehensible just decades ago. The same principles that govern these complex maneuvers also apply to some of the most routine operations in space. Every time the International Space Station needs to avoid space debris, controllers plan a carefully timed engine burn that raises or lowers the station's orbit by just a few miles. These debris avoidance maneuvers happen several times per year, each one requiring precise calculations to ensure the station remains in the correct orbit for visiting spacecraft. The mathematics involved in these calculations would fill textbooks, but the underlying concept is beautifully simple. Everything in space moves in predictable patterns governed by gravity and momentum. Once you understand these patterns, you can plan trajectories that accomplish seemingly impossible feats with minimal energy expenditure. This predictability is what makes long-term space missions possible. When we launch a spacecraft toward Jupiter, we're betting that our understanding of orbital mechanics is accurate enough to predict where Jupiter will be several years in the future. It's a bet we've won repeatedly, but it requires confidence in mathematical models that describe the behavior of objects across billions of miles and many years of time. The confidence comes from centuries of astronomical observations and theoretical development. Every successful space mission validates our understanding of celestial mechanics and builds confidence for even more ambitious future missions. When Voyager 2 arrived at Neptune, exactly when and where mission planners predicted, it wasn't just a triumph of engineering. It was a confirmation that our mathematical models of the solar system are remarkably accurate. But space travel isn't just about following predictable orbits. Sometimes spacecraft must adapt to unexpected situations, demonstrating the ingenuity of both their designers and the mission teams that operate them. When the main antenna on the Galileo spacecraft failed to deploy properly, engineers developed new communication techniques that allowed the mission to return valuable scientific data despite operating with a severely compromised communications system. Similarly, when one of the reaction wheels on the Kepler Space Telescope failed, threatening to end the planet hunting mission, engineers developed a technique that used solar pressure to help stabilize the spacecraft. They essentially turned a mechanical failure into an opportunity to demonstrate new methods of spacecraft control. These examples illustrate an important principle of space exploration. Spacecraft must be designed not just to operate under ideal conditions, but to adapt and survive when things go wrong. In the harsh environment of space, failures are inevitable. The key to successful missions is building in redundancy and flexibility that allows spacecraft to continue operating even when critical systems fail. This philosophy of resilient design extends to every aspect of spacecraft engineering. Power systems have backup power sources. Communication systems have multiple antennas and transmission paths. Navigation systems have redundant sensors and independent methods of determining position and orientation. The goal is to ensure that no single failure can end a mission. But perhaps the most important backup system is the creativity and problem-solving ability of the mission teams on Earth. When Apollo 13 suffered its famous explosion, the the spacecraft's survival depended not just on its backup systems, but on the ingenuity of engineers who figured out how to make a square carbon dioxide scrubber fit into a round hole using only materials available on the spacecraft. This human element remains crucial to space exploration, even as our spacecraft become increasingly autonomous. While modern spacecraft can execute complex sequences of operations without human intervention, they still depend on human oversight and decision-making for their most critical operations. The balance between automation and human control varies depending on the mission. Spacecraft exploring the outer solar system must be largely autonomous, because radio signals take hours to travel between Earth and the spacecraft. There's no possibility of real-time control when Jupiter is over an hour away at the speed of light. These spacecraft must be programmed to make decisions independently, using artificial intelligence systems that can respond to unexpected situations without waiting for instructions from Earth. In contrast, spacecraft operating near Earth can benefit from more direct human control. The Hubble Space Telescope, for example, receives detailed pointing instructions several times per day, allowing astronomers to direct its observations based on the latest scientific priorities and discoveries. This spectrum of autonomy reflects a fundamental challenge of space exploration. As we venture farther from Earth, our spacecraft must become increasingly independent. Future missions to the outer planets will require even more sophisticated artificial intelligence systems capable of making complex decisions about scientific observations, navigation, and system management. The development of these autonomous systems is teaching us valuable lessons about decision-making in extreme environments. Spacecraft operating in the outer solar system face conditions that no human has ever experienced. They must function in radiation fields that would be lethal to humans at temperatures that would freeze most materials, with power sources that provide only a fraction of the energy available on Earth. Yet these machines continue to function and return valuable scientific data. The New Horizons spacecraft, which flew past Pluto in 2015, had been traveling for over 9 years when it reached its destination. During that time, it hibernated for most of the journey to conserve power and reduce wear on its systems. But when it woke up for its encounter with Pluto, it performed flawlessly, returning images and data that revolutionized our understanding of the dwarf planet. This ability to hibernate for years and then awaken to perform complex operations represents a remarkable achievement in spacecraft design. It's like building a machine that can sleep for a decade and then wake up refreshed and ready to work. The engineering challenges involved in creating such systems are immense, requiring components that can withstand years of dormancy without degrading. The power systems alone present extraordinary challenges. Solar panels become less effective as spacecraft travel farther from the Sun. At Jupiter's distance, sunlight is 25 times weaker than at Earth. At Saturn, it's 100 times weaker. Beyond Saturn, solar power becomes impractical, and spacecraft must rely on nuclear power sources. These radioisotope thermoelectric generators, or RTGs, convert the heat from radioactive decay directly into electricity. They provide steady power for decades, but they also represent some of the most carefully regulated technology in space exploration. The radioactive materials must be contained in systems designed to survive launch accidents, atmospheric re-entry, and any other conceivable failure mode. The use of nuclear power in space missions reflects the extraordinary lengths we go to in order to explore the solar system. When we launch a spacecraft powered by plutonium, we're making a commitment that extends for decades. The Voyager spacecraft will continue to operate on nuclear power until sometime in the 2020s, over 40 years after their launch. This longevity creates unique opportunities for scientific discovery. Spacecraft that were designed to study one planet or phenomenon often provide unexpected insights into completely different aspects of the solar system. Voyager 1, originally designed to study Jupiter and Saturn, became the first human-made object to enter interstellar space. Its instruments, still functioning after 4 decades, are now providing our first direct measurements of the space between stars. Similarly, the Cassini spacecraft, designed primarily to study Saturn, made numerous discoveries about the planet's moons that were never part of its original mission plan. When scientists realized that the moon Enceladus was ejecting water vapor from its south pole, they redesigned parts of the mission to fly through these geysers and analyze their composition. These serendipitous discoveries highlight one of the most exciting aspects of space exploration. While we plan missions to answer specific questions, the universe often surprises us with phenomena we never expected to find. Every spacecraft becomes an explorer in the truest sense, venturing into unknown territory where anything might be discovered. But perhaps the most profound aspect of spacecraft travel is how it changes our perspective on our place in the universe. When we see images of Earth taken from spacecraft visiting other planets, we're reminded of how small and precious our world really is. The famous pale blue dot image taken by Voyager 1 from beyond Neptune shows Earth as a tiny speck suspended in a sunbeam, a humbling reminder of our cosmic insignificance and cosmic responsibility. These perspectives from space have fundamentally changed how we think about our planet and our species. They've shown us that Earth's atmosphere is a thin, fragile shell surrounding our world. They've revealed the interconnectedness of Earth's climate systems and the delicate balance that maintains conditions suitable for life. They've demonstrated that national boundaries are invisible from space and that we truly are all passengers on the same small spacecraft, traveling through the cosmos. As our spacecraft venture farther from Earth, they carry with them not just scientific instruments, but human hopes and dreams. They represent our species' first tentative steps toward becoming a spacefaring civilization. Each successful mission builds the knowledge and confidence needed for even more ambitious journeys in the future. The techniques we're developing for robotic spacecraft travel will eventually enable human exploration of the solar system. The same orbital mechanics that guide our robotic probes will guide human expeditions to Mars and beyond. The same life support systems that keep spacecraft functioning for decades will be adapted to keep human explorers alive during long journeys through space. But human space travel will also require new technologies and techniques that go far beyond what we need for robotic missions. Humans need air, water, food, and protection from radiation. They need psychological support during long periods of isolation. They need medical care and emergency response capabilities. They need the ability to return safely to Earth after journeys that may last years. These challenges are driving innovations in closed-loop life support systems, radiation shielding, artificial gravity systems, and autonomous medical systems. Each technological advance brings us closer to the day when humans will routinely travel throughout the solar system, establishing permanent outposts on other worlds and expanding the reach of human civilization beyond Earth. As we continue our gentle drift through these cosmic concepts, remember that every spacecraft mission is ultimately a human story. Behind every successful journey through space are thousands of people who dedicated years of their lives to making it possible. Engineers who solved problems that had never been solved before. Scientists who designed instruments to answer questions about worlds they would never visit. Mission controllers who guided spacecraft across billions of miles with precision measured in meters. These human stories remind us that space exploration is not just about technology and mathematics. It's about curiosity, determination, and the fundamental human drive to understand our place in the universe. Every spacecraft we launch carries with it the hopes and dreams of our entire species, representing our collective desire to explore, discover, and expand the boundaries of human knowledge. Tonight, as you settle deeper into contemplation of these cosmic journeys, know that above your head, dozens of spacecraft are silently gliding through space, following trajectories planned years ago, carrying out missions that will expand human knowledge for generations to come. They are our ambassadors to the cosmos, representing the best of human ingenuity and curiosity as they dance through the gravitational fields of distant worlds. In their elegant trajectories and patient journeys, they embody the very essence of space travel, not as a conquest of space, but as a joining of the ancient cosmic dance that connects all matter and energy throughout the universe. And in learning to dance with the cosmos, we take our first steps toward becoming truly cosmic beings ourselves. The story of how we navigate these cosmic pathways becomes even more fascinating when we consider the invisible networks that connect our spacecraft to Earth. Right now, as you rest in the quiet of your evening, a vast array of radio dishes scattered across our planet are listening to the whispers of distant machines. These signals, traveling at the speed of light, carry precious cargo, not gold or diamonds, but something far more valuable. Information. Picture the Goldstone Deep Space Communications Complex in California's Mojave Desert. In the stillness of the desert night, massive antennas slowly track across the sky, following invisible points of light that represent our most distant explorers. These dishes, some as large as football fields, capture radio waves so faint that the total power received from all our interplanetary spacecraft combined wouldn't light a single Christmas tree bulb. Yet within these whisper-quiet signals lies everything. The health of the spacecraft, the discoveries it's making, the images of alien worlds it's capturing. When the New Horizons spacecraft flew past Pluto, every pixel of those historic images had to travel over 4 billion miles to reach us, taking 4.5 hours at the speed of light. Imagine taking a photograph and then waiting nearly 5 hours to see what you captured. This communication challenge grows more profound with distance. When we eventually send spacecraft to the nearest stars, the radio delay will be measured not in hours, but in years. A simple question sent to such a probe might not receive an answer until the person who asked it has grown old and grey. This forces us to design spacecraft that can think for themselves, making decisions about exploration and discovery without human guidance. But even within our solar system, the communication delays create fascinating challenges. When the Curiosity rover landed on Mars, mission controllers on Earth couldn't provide real-time guidance during the crucial final minutes. The rover had to execute its complex landing sequence autonomously, using pre-programmed instructions to navigate the famous 7 minutes of terror between entering Mars' atmosphere and touching down safely. This delayed communication creates a strange intimacy between spacecraft and their human operators. Controllers must learn to think like they're distant machines, anticipating problems and preparing solutions for situations that might not occur for hours or days. It's like having a conversation with someone on the other side of the world, but stretched across the dimensions of space and time. The data that flows through these cosmic communication networks tells stories that would make poets weep. Every day, our spacecraft send back measurements of magnetic fields that surround distant planets, chemical analyses of ancient rocks on Mars, images of storms larger than Earth swirling in Jupiter's atmosphere. They're writing the first chapters of a new kind of literature, the literature of direct exploration. But perhaps most remarkably, these communications reveal the profound patience required for space exploration. When scientists want to change a spacecraft's mission plan, they might need to upload new software across hundreds of millions of miles. The upload could take days or weeks, and then they must wait for confirmation that the changes were received correctly. It's like trying to teach someone a new skill by sending letters that take months to deliver. This patience extends to every aspect of space mission operations. Consider the process of taking a single photograph with the Hubble Space Telescope. First, astronomers submit their observing proposals months or years in advance. If approved, the observation is scheduled into Hubble's timeline. Then, at the precise moment planned, the telescope must point to an exact location in space, stabilize itself to within a tiny fraction of an arcsecond, and hold that position while photons from distant galaxies slowly accumulate on its detectors. The resulting image might represent just a few hours of observation, but it could reveal galaxies that formed when the universe was young, their light traveling for billions of years to reach Hubble's mirrors. In that single photograph lies a kind of time travel, showing us the cosmos as it existed long before Earth was even formed. This ability to capture ancient light reveals one of the most beautiful aspects of space exploration. Every observation is also a journey through time. When we look at Saturn through our spacecraft's cameras, we're not just seeing another planet, we're seeing light that left Saturn's clouds just minutes or hours ago, depending on the distance. When we observe distant galaxies, we're looking billions of years into the past, witnessing the universe as it was when it was young and newly formed. Our spacecraft have become time machines, not in the science fiction sense, but in the profound reality of cosmic observation. They carry our eyes and instruments to vantage points throughout the solar system, each providing a unique perspective on the flow of time and the evolution of worlds. From these scattered observation posts, we've discovered that time itself moves differently throughout the solar system. Clocks aboard spacecraft near massive planets tick slightly slower than identical clocks on Earth, exactly as Einstein predicted. The GPS satellites orbiting our planet must constantly adjust their timing to account for these relativistic effects. Without these corrections, GPS navigation would be off by miles within hours. But the most profound temporal effects occur near the most massive objects. If we could somehow place a clock near the event horizon of a black hole and compare it to a clock on Earth, we would see time dilation effects so extreme that what seems like hours near the black hole might correspond to years on Earth. Our spacecraft, in visiting the gravitational fields of different planets, experience these effects in miniature, their atomic clocks recording the subtle variations in the flow of time throughout the solar system. These discoveries transform how we think about space travel itself. We're not just moving through space. We're moving through space-time, that unified fabric where space and time are woven together. Every trajectory our spacecraft follow carves a path not just through three-dimensional space, but through the four-dimensional reality of space-time itself. This four-dimensional perspective reveals why some spacecraft trajectories seem to violate common sense. When the Parker Solar Probe was launched toward the Sun, it first flew away from our star, using a gravity assist from Venus to reshape its orbit. From a three-dimensional perspective, this seems inefficient. But in four-dimensional space-time, this trajectory represents the most elegant path to the probe's ultimate destination in the Sun's corona. The probe's journey illustrates another remarkable aspect of spacecraft travel. As it approaches the Sun, it will experience temperatures exceeding 2,000 degrees Fahrenheit, yet its instruments will remain cool behind a specially designed heat shield. The spacecraft must also deal with increasingly intense radiation and solar wind particles that could damage its electronics. But perhaps most challenging is the communication blackout that occurs when the probe passes behind the Sun from Earth's perspective. During these periods, the spacecraft operates completely autonomously, making its own decisions about instrument operations and spacecraft health. It's like sending an explorer into a cave with no possibility of communication, trusting that they will emerge safely with valuable discoveries. These communication blackouts occur regularly throughout the solar system as planets and moons move between our spacecraft and Earth. During superior conjunction, when Mars passes behind the Sun, all communication with Mars missions is suspended for weeks. Mission controllers must plan these communication gaps months in advance, ensuring that spacecraft have enough pre-programmed instructions to operate safely during the blackout periods. The planning required for these operations reveals the intricate choreography of space mission design. Controllers must account not just for the orbital positions of planets and spacecraft, but also for the rotation of Earth, which determines which ground stations can communicate with which spacecraft at any given time. The Deep Space Network uses stations in California, Spain, and Australia to ensure that at least one antenna can always communicate with distant spacecraft as Earth rotates. This global network of communication creates a kind of nervous system for our expanding presence in space. Data flows continuously between spacecraft and Earth, carrying scientific observations, engineering telemetry, and navigation updates. Mission controllers can monitor the health of dozens of spacecraft simultaneously, adjusting their operations based on changing conditions throughout the solar system. But the most remarkable aspect of this cosmic communication network is its fragility. These signals, carrying humanity's most ambitious scientific discoveries, must compete with interference from Earth's own radio emissions, solar storms that can disrupt communications for days, and the simple geometric challenge of maintaining contact across billions of miles. Sometimes, the solutions to these communication challenges require extraordinary creativity. When the Galileo spacecraft's main antenna failed to deploy, engineers developed new data compression techniques that allowed the mission to return valuable scientific data using only a small backup antenna. They essentially taught the spacecraft to whisper more efficiently, maximizing the information content of every precious bit transmitted across the vast distance to Jupiter. These innovations in space communication often find applications back on Earth. The data compression techniques developed for space missions have improved internet communications. The error correction methods used to ensure accurate data transmission across interplanetary distances have enhanced cellular phone networks. Space exploration drives technological advancement that benefits all of humanity. But beyond the technological achievements, spacecraft communication represents something profoundly human. Every signal received from a distant probe is a message from the frontier of human exploration. These spacecraft are our eyes and ears in places no human has ever been, sending back reports from the edge of our understanding. When the Cassini spacecraft transmitted its final signal as it dove into Saturn's atmosphere, mission controllers knew they were receiving the last words from a faithful explorer that had served for over 13 years. The spacecraft had become more than just a machine. It had become a member of the team, a trusted companion that had shared in the excitement of discovery and the satisfaction of successful exploration. This emotional connection between humans and their spacecraft reveals something beautiful about the nature of exploration itself. These machines carry with them not just scientific instruments, but human curiosity, determination, and wonder. They extend our senses across the solar system, allowing us to touch the moons of Jupiter, taste the atmosphere of Venus, and feel the magnetic fields of distant planets. In their patient journeys through space, spacecraft embody the best qualities of human exploration. They demonstrate persistence in the face of mechanical failures, adaptability when missions change, and the courage to venture into unknown territories where anything might be discovered. They show us that exploration is not about conquest or domination, but about understanding and connection. As our spacecraft continue their journeys through the cosmic ocean, they're writing new chapters in the story of human exploration. Each successful mission builds the foundation for even more ambitious journeys in the future. The techniques we're perfecting today will enable missions to the moons of Jupiter and Saturn, to the asteroids and comets that preserve the solar system's earliest history, and eventually to the stars themselves. But perhaps most importantly, these spacecraft are changing how we see ourselves and our place in the universe. They're showing us that Earth is not isolated in space, but part of a vast, interconnected system of worlds. They're revealing that the same physical laws that govern the motion of planets also govern the behavior of atoms, connecting the cosmic scale to the quantum realm in ways we're only beginning to understand. Tonight, as you settle deeper into contemplation of these cosmic journeys, remember that you are connected to every spacecraft exploring the solar system. You share the same star, breathe atoms forged in the stellar cores, and participate in the same gravitational dance that guides our robotic explorers across billions of miles. In their elegant trajectories and patient discoveries, our spacecraft embody humanity's greatest aspirations. They represent our refusal to accept the boundaries of our birth world, our determination to explore and understand, and our deep conviction that the universe is not just something to observe from a distance, but something to experience directly through the extension of our capabilities across space and time. As these mechanical ambassadors continue their journeys through the solar system and beyond, they carry with them the hopes and dreams of our entire species. They are the first tentative steps of a civilization learning to dance with the cosmos itself. preparing for the day when humans will follow in their wake to establish permanent outposts among the stars. The gentle art of spacecraft travel is teaching us to think in cosmic terms, to plan for decades and centuries, to work with the fundamental forces of nature rather than against them. In learning to navigate the gravitational currents of space, we're not just developing technology, we're developing wisdom, patience, and a profound appreciation for the elegant mathematics that govern the motion of everything from subatomic particles to galaxy clusters. And in that growing wisdom lies the promise of our future as a spacefaring species, forever dancing through the cosmic ocean on trajectories of discovery that stretch toward infinity itself. Tonight, as we drift deeper into the mechanics of cosmic travel, we encounter something that might seem paradoxical. The fastest spacecraft we've ever built moves slower than a snail compared to the speeds that nature routinely achieves throughout the universe. Yet within this apparent limitation lies one of the most beautiful insights about our place in the cosmic dance. Consider the Voyager spacecraft, humanity's fastest messengers to the stars. They're racing away from the sun at over 38,000 miles per hour, speeds that would carry you around Earth in just over an hour. Yet at this breakneck pace, it will take them over 70,000 years to reach the nearest star. The universe is so vast that even our greatest achievements in speed become whispers in the cosmic wind. But here's what makes this truly remarkable. Those seemingly glacial interstellar journeys reveal something profound about the nature of space travel itself. We're not just moving through empty space. We're navigating currents of gravity, magnetic fields, and radiation that flow between the stars like invisible rivers. Our spacecraft become boats on these cosmic streams, carried by forces that dwarf anything we can generate with our engines. The interstellar medium, that supposedly empty space between stars, turns out to be filled with charged particles, magnetic fields, and shock waves from stellar explosions. As our spacecraft venture beyond the influence of the sun, they encounter these interstellar winds for the first time in human history. The Voyager probes have become our first weather stations in this alien ocean, sending back reports of conditions that no Earth-based observatory could ever measure. These measurements reveal that space travel isn't just about overcoming distance. It's about learning to read the invisible landscape of forces that shape the galaxy itself. Future interstellar missions will need to navigate not just the gravitational fields of stars, but the complex magnetic geography of the galaxy, the shock waves from ancient supernovae, and the subtle currents of dark matter that we're only beginning to detect. But even within our solar system, we're discovering that spacecraft travel involves navigating forces we never anticipated. The solar wind, that stream of charged particles flowing outward from the sun, creates pressure that can actually propel lightweight spacecraft. Solar sails exploit this pressure, using enormous gossamer sheets to catch the solar wind like ancient mariners caught ocean breezes. The physics of solar sailing reveals something beautiful about the interconnectedness of space and energy. Photons from the sun carry momentum as well as energy. When they strike a reflective surface, they transfer that momentum, creating thrust. It's like being pushed by light itself, propelled by the same sunshine that warms your face on a summer day. This photon pressure is incredibly gentle. The force exerted by sunlight on a solar sail is roughly equivalent to the weight of a paperclip pressing on your palm. Yet in the frictionless environment of space, this whisper-quiet thrust can gradually accelerate a spacecraft to remarkable velocities. Over months and years, light pressure can achieve what chemical rockets accomplish in minutes, but with unlimited endurance and no fuel consumption. The mathematics of solar sailing become particularly elegant when we consider how the force changes with distance from the sun. As spacecraft travel farther from our star, the solar wind pressure decreases with the square of the distance. But this predictable variation allows mission planners to calculate precisely how a solar sail's trajectory will evolve over time, creating opportunities for missions that would be impossible with conventional propulsion. Some of the most ambitious future missions envision using solar sails to reach the outer planets faster than any chemical rocket could manage. By starting close to the Sun where solar pressure is strongest, then gradually spiraling outward, these spacecraft could build up tremendous velocities while using no fuel whatsoever. They would literally surf the solar wind to distant worlds, riding waves of light and charged particles across the solar system. But solar sails represent just one example of how spacecraft designers are learning to harness the natural forces of space. Magnetic sails could use the spacecraft's own magnetic field to interact with the solar wind, creating thrust without any physical sail at all. These invisible magnetic structures would push against charged particles in space, propelling the spacecraft forward while remaining completely intangible. Even more exotic propulsion concepts emerge when we consider the quantum nature of empty space itself. The vacuum of space isn't truly empty. It's filled with virtual particles that pop into existence and annihilate each other in timeframes so brief they barely qualify as real. Yet some theoretical propulsion systems propose tapping into this quantum foam, extracting energy from the very structure of space-time itself. These concepts remain far beyond our current technology, but they illustrate how our understanding of space travel continues to evolve. Each new discovery in physics opens possibilities we never imagined. What seems impossible today may become routine tomorrow, just as rocket travel seemed impossible to previous generations. But perhaps the most profound evolution in spacecraft travel involves learning to work with time itself. Einstein showed us that time is not absolute, but relative, flowing at different rates depending on velocity and gravity. As our spacecraft approach significant fractions of the speed of light, they would experience time dilation effects that stretch seconds into years from the perspective of Earth-based observers. This creates fascinating possibilities for future interstellar missions. A spacecraft accelerating to near-light speed could reach nearby stars within the lifetime of its human crew. Even though centuries might pass on Earth during the journey, the travelers would return to find a world transformed by time, their brief voyage having spanned generations for those left behind. These relativistic effects aren't just theoretical curiosities. They're already measurable in our fastest spacecraft. The atomic clocks aboard GPS satellites must be adjusted for relativistic effects, or navigation errors would accumulate within hours. Every spacecraft we launch experiences tiny time dilation effects as it moves through the curved spacetime around Earth and the Sun. But time dilation also creates opportunities for spacecraft design. Processes that seem impossibly slow from our Earthbound perspective might appear rapid to a spacecraft traveling at high velocity. Radioactive decay rates would appear slower, potentially extending the lifetime of nuclear power sources. Even the degradation of spacecraft components might be slowed by relativistic effects. This intimate relationship between motion and time transforms how we think about long-duration space missions. We're not just sending spacecraft across space, we're sending them through time, navigating the four-dimensional landscape of space-time itself. Every trajectory becomes a path through both space and time, with each choice affecting not just where the spacecraft goes, but when it arrives. The planning required for these temporal trajectories adds layers of complexity that challenge our understanding of cause and effect. Mission controllers must account for communication delays that change as spacecraft move through curved spacetime. They must predict not just where planets will be, but how the flow of time itself will be affected by the gravitational fields the spacecraft encounters. But perhaps most remarkably, these relativistic effects create opportunities for what we might call temporal exploration. By carefully choosing trajectories that pass close to massive objects, spacecraft could experience time dilation effects that allow them to sample different rates of temporal flow. They could visit regions where time moves slowly relative to Earth, then return to regions where time flows more rapidly, creating a kind of time travel through the natural geometry of space-time. These possibilities seem like science fiction, but they emerge naturally from our current understanding of physics. As our spacecraft venture to increasingly extreme environments, they will inevitably encounter regions where relativistic effects become significant. The spacecraft that eventually explore the vicinity of black holes will experience time dilation so extreme that minutes near the event horizon correspond to hours or days at safe distances. The data transmitted by such spacecraft would carry more than scientific measurements. They would carry information about the nature of time itself, revealing how the universe looks from vantage points where the familiar flow of temporal causality becomes stretched and distorted. These missions would be explorations not just of space, but of the fundamental structure of reality. Yet even as we contemplate these exotic possibilities, the most profound spacecraft journeys remain those that reveal the beauty and complexity of ordinary celestial mechanics. Every successful orbital insertion, every precise planetary flyby, every delicate course correction demonstrates our growing mastery of the gravitational arts. We're learning to read the invisible sheet music of orbital dynamics, conducting symphonies of motion that span years and traverse billions of miles. This growing expertise enables missions of increasing ambition and complexity. The techniques we've perfected for single spacecraft missions now allow us to coordinate the movements of multiple spacecraft working together. Formation flying missions use several spacecraft to create virtual instruments larger than any single probe could carry. These distributed observatories can measure phenomena that require simultaneous observations from multiple vantage points. The European Space Agency's cluster mission demonstrated this concept by using 4 identical spacecraft to study Earth's magnetosphere. Flying in carefully controlled formations, these spacecraft could distinguish between spatial and temporal variations in magnetic fields, solving observational problems that had puzzled scientists for decades. The success of Cluster has inspired even more ambitious formation flying concepts for future missions. Some proposed missions would use dozens or even hundreds of small spacecraft working in coordination. These swarms of tiny probes could explore asteroid fields, study the solar wind in 3 dimensions, or create synthetic aperture telescopes with resolution far exceeding what any single mirror could achieve. The challenge lies not just in building these miniature spacecraft, but in coordinating their movements with the precision required for scientific observations. The mathematics of formation flying require solving the gravitational 3-body problem in real time, accounting for the perturbations caused by planets, moons, and even the solar wind pressure on each individual spacecraft. Mission controllers must choreograph these cosmic ballets with precision measured in meters across distances of thousands of miles, maintaining formations that drift slowly through space while preserving the geometric relationships needed for scientific observations. But perhaps the most elegant formation flying concept involves spacecraft that maintain their relative positions using only gravitational forces. By carefully choosing their orbital parameters, multiple spacecraft can remain in stable configurations for years without any fuel expenditure. These gravitational formations would be sculpted by the same forces that shape planetary rings and asteroid families, using natural dynamics to maintain artificial structures. The techniques developed for formation flying are already inspiring new approaches to single spacecraft missions. Instead of building one large, complex spacecraft, mission designers are learning to distribute functionality across multiple smaller platforms. This approach provides redundancy, allows for specialized instruments on each platform, and reduces the catastrophic risk of single-point failures. These distributed mission concepts reflect a broader evolution in spacecraft design philosophy. Rather than creating monolithic machines that attempt to accomplish everything, we're learning to build systems that can adapt, evolve, and respond to unexpected discoveries. Modular spacecraft designs allow for in-flight reconfiguration of instruments and capabilities. Software updates can completely change a mission's objectives years after launch. This flexibility proves crucial when spacecraft encounter phenomena that their designers never anticipated. The ability to reprogram instruments, adjust observation sequences, and even change fundamental mission objectives has enabled some of our greatest discoveries. When Cassini detected water vapor plumes from Enceladus, the mission team was able to redirect the spacecraft to fly through these plumes and analyze their composition, discovering evidence for a subsurface ocean that might harbor life. These serendipitous discoveries highlight one of the most exciting aspects of spacecraft exploration. While we launch missions to answer specific questions, the universe often surprises us with phenomena we never expected to find. Every spacecraft becomes a discoverer in the truest sense, venturing into territories where anything might be waiting. The history of space exploration is filled with these unexpected discoveries. Mariner 10's gravity assist trajectory past Venus revealed that the planet rotates backward compared to most other planets. The Voyager flybys discovered active volcanism on Io, intricate structure in Saturn's rings, and geysers of nitrogen on Triton. The Galileo mission found strong evidence for subsurface oceans on Europa, completely changing our understanding of where life might exist in the solar system. Each of these discoveries required not just sophisticated instruments, but spacecraft capable of responding to unexpected opportunities. Mission teams had to quickly develop new observation strategies, reprogram instruments for phenomena they had never studied, and adjust spacecraft trajectories to optimize encounters with newly discovered features. This adaptability has become a defining characteristic of successful space missions. The most productive spacecraft are those designed not just to execute predetermined observation sequences, but to respond intelligently to whatever they find. They must be capable of recognizing interesting phenomena and adjusting their operations accordingly, often without waiting for instructions from Earth. The development of this autonomous decision-making capability represents one of the most significant advances in spacecraft technology. Modern spacecraft carry artificial intelligence systems that can evaluate the scientific importance of their observations, prioritize data transmission based on available bandwidth, and even identify potentially hazardous situations that require immediate attention. These AI systems must operate under constraints that no terrestrial computer ever faces. They have extremely limited computational power, must function reliably for years without maintenance, and operate in radiation environments that would destroy most electronics. Yet they must make decisions about scientific observations that could determine the success or failure of billion-dollar missions. The algorithms that enable this autonomous operation represent a fascinating intersection of computer science and space exploration. Machine learning systems trained on Earth must adapt to completely alien environments. Pattern recognition software must identify geological features on worlds that may be unlike anything in their training data. Decision-making algorithms must balance competing priorities with incomplete information and uncertain outcomes. But perhaps most remarkably, these artificial intelligence systems are learning to exhibit something approaching scientific curiosity. They can recognize when they've observed something unusual and autonomously adjust their observation strategies to gather more information. They're becoming electronic explorers, driven by programmed goals, but capable of independent discovery. This evolution toward autonomous exploration reflects a deeper truth about the nature of space travel. As our spacecraft venture farther from Earth, they must become increasingly independent. The communication delays involved in interstellar travel will require spacecraft that can conduct entire scientific investigations without human guidance, making discoveries and following up on interesting phenomena across decades of autonomous operation. Future interstellar probes will need to embody not just human engineering capability, but human scientific instincts. They must be curious about what they find, persistent in investigating puzzling phenomena, and creative in developing new approaches to unexpected challenges. In a sense, they will carry human consciousness to the stars, representing our species in encounters with completely alien environments. The technology we're developing for this autonomous exploration will inevitably transform life on Earth as well. Artificial intelligence systems capable of making scientific discoveries in the depths of space will find applications in medical research, environmental monitoring, and countless other fields. The challenges of space exploration drive innovations that benefit all of humanity. But beyond the technological achievements, autonomous spacecraft represent something profoundly philosophical. They embody human curiosity in mechanical form, carrying our desire to explore and understand to places we may never visit ourselves. They are extensions of human consciousness, mechanical minds capable of wonder and discovery. As these artificial explorers venture into the cosmic ocean, they carry with them the accumulated knowledge and wisdom of our entire species. Every successful mission adds to their capabilities. Every discovery refines their understanding. Every challenge overcome strengthens their ability to adapt and survive in alien environments. Tonight, as you drift deeper into contemplation of these cosmic journeys, remember that above your head, mechanical minds are making decisions about exploration and discovery. They're following trajectories planned by human intelligence, but adapted by artificial minds capable of independent thought. They represent a new form of consciousness, emerging from the marriage of human curiosity and cosmic exploration. In their patient journeys through space, these spacecraft embody humanity's greatest aspiration, the desire to understand our place in the universe and to extend the reach of consciousness beyond the boundaries of our birth world. They are the first tentative steps toward a future where intelligence, both human and artificial, will explore the galaxy in partnership, dancing together through the cosmic ocean on trajectories of discovery that stretch toward infinity itself. The spacecraft that will explore the outer reaches of our solar system must also contend with something we rarely consider here on Earth: the profound loneliness of the cosmic void. Not loneliness in any emotional sense, but the physical isolation that comes from being the only human-made object within billions of cubic miles of empty space. Consider what this means for spacecraft design. On Earth, we're surrounded by a vast technological ecosystem. When something breaks, we can call for help, order replacement parts, or simply drive to a store. But a spacecraft beyond Saturn exists in a realm where the nearest help is literally years away at the speed of light. Every component must be designed not just to work, but to work perfectly for decades without any possibility of repair or maintenance. This isolation drives innovations that seem almost magical in their ingenuity. Spacecraft carry multiple backup systems for every critical function. They have redundant computers, duplicate instruments, and backup methods for generating power and maintaining communication. Some spacecraft can even reconfigure themselves, shutting down failed components and rerouting their functions through working systems. But the most remarkable adaptation to cosmic isolation is how spacecraft learn to heal themselves. Advanced diagnostic systems monitor thousands of parameters continuously, detecting the early signs of component degradation before failures occur. When problems are identified, onboard systems can often compensate automatically, adjusting operating parameters to extend component lifetimes, or switching to backup systems before primary systems fail completely. The New Horizons mission provides a beautiful example of this self-reliance. During its 9-year journey to Pluto, the spacecraft hibernated for most of the trip to preserve its systems, but it would periodically wake itself up, perform health checks on all its components, and send status reports to Earth. If it detected any problems, it could begin corrective actions long before ground controllers even knew an issue existed. This ability to operate independently for years at a time requires a fundamental shift in how we think about machine intelligence. These spacecraft must be programmed not just to execute predetermined sequences, but to adapt to changing conditions, respond to unexpected situations, and make decisions about their own survival and mission success. The software systems that enable this autonomy are marvels of engineering in their own right. They must be absolutely reliable, capable of running for decades without crashes or failures. They must be efficient enough to operate on the minimal computational resources available in space-qualified hardware. And they must be flexible enough to handle situations that their programmers never anticipated. But perhaps most importantly, these software systems must embody something approaching wisdom. They must know when to take risks and when to play it safe. They must balance the scientific value of observations against the operational risks of obtaining them. They must decide how to allocate limited resources like power, memory, and communication bandwidth across competing priorities. This electronic wisdom emerges from decades of collective experience in space exploration. Every mission failure teaches lessons that get incorporated into future spacecraft designs. Every unexpected situation encountered by one mission becomes part of the knowledge base that informs the autonomous systems of future missions. Our spacecraft are becoming progressively more intelligent, not just through advances in computer technology, but through the accumulated wisdom of space exploration itself. The Deep Impact mission illustrates this beautifully. The spacecraft was designed to fire a projectile into a comet and observe the resulting explosion. But when the projectile struck Comet Tempel 1, it created a debris cloud that temporarily blinded the spacecraft's cameras. The onboard systems recognized this situation and automatically adjusted the observation sequence, continuing to collect valuable data despite the unexpected interference. This kind of adaptive behavior requires spacecraft to understand not just what they're supposed to do, but why they're doing it. They must grasp the scientific objectives of their missions well enough to make intelligent decisions when the predetermined plan encounters unexpected realities. They're developing something approaching scientific intuition, the ability to recognize what's important and adjust their actions accordingly. But the isolation of space creates challenges that go beyond technical reliability. Spacecraft must also cope with the gradual degradation that comes with age and exposure to the harsh environment of space. Solar panels lose efficiency over time as they're bombarded by high-energy particles. Electronic components slowly degrade under constant radiation exposure. Mechanical systems suffer from the thermal cycling between extreme heat and cold. Yet remarkably, many spacecraft far exceed their planned lifetimes. The Opportunity rover on Mars was designed for a 90-day mission, but operated for over 14 years. The Cassini spacecraft at Saturn functioned perfectly for 13 years beyond its original 4-year mission plan. These extended missions become possible partly through careful engineering, but also through the spacecraft's ability to adapt to their own aging. As systems degrade, spacecraft learn to work around their limitations. They might operate instruments at reduced power levels to extend their lifetimes. They might adjust their pointing accuracy to compensate for degraded attitude control systems. They might change their communication schedules to account for weakening radio transmitters. The spacecraft essentially learn to grow old gracefully, maintaining their scientific productivity even as their physical capabilities diminish. This graceful aging process reveals something profound about the nature of exploration itself. The most valuable discoveries often come not from perfect systems operating under ideal conditions, but from adaptive systems that can continue functioning despite accumulated wear and unexpected challenges. The spacecraft that make the greatest contributions to human knowledge are often those that learn to thrive in adversity. The Voyager spacecraft exemplify this resilience. After more than 4 decades in space, they continue to transmit valuable scientific data despite the failure of numerous systems. Their radioisotope power sources are slowly decaying, providing less electricity each year. Some of their instruments have failed. Their attitude control systems are operating far beyond their design specifications. Yet they persist, sending back humanity's first direct observations of interstellar space. This persistence in the face of degradation has become one of the defining characteristics of successful space missions. Mission teams have learned to plan not just for nominal operations, but for graceful degradation modes that allow spacecraft to continue contributing to science even as their capabilities diminish. They design missions that can adapt their objectives as systems fail, ensuring that valuable observations continue until the very end. The planning for these extended missions requires a kind of temporal architecture that spans decades. Mission designers must anticipate how spacecraft will age, which systems are likely to fail first, and how the mission can adapt to various failure scenarios. They create decision trees that stretch years into the future, preparing for contingencies that may not occur until long after the original mission team has moved on to other projects. This long-term thinking reflects a deeper evolution in how we approach space exploration. We're learning to think not just about individual missions, but about the cumulative knowledge that emerges from decades of sustained exploration. Each spacecraft becomes part of a larger observatory distributed throughout the solar system, with different platforms providing complementary observations of cosmic phenomena. The coordination required for these multi-mission observations challenges our traditional concepts of space mission management. Data from spacecraft at Mars must be correlated with observations from probes at Jupiter, measurements from solar observatories, and monitoring from Earth-based instruments. The solar system becomes a single integrated laboratory where phenomena can be studied from multiple vantage points simultaneously. This distributed approach to exploration enables scientific investigations that no single spacecraft could accomplish alone. When solar storms erupt from the Sun, they can be tracked by spacecraft positioned throughout the solar system, providing three-dimensional views of how these disturbances propagate through interplanetary space. When comets approach the inner solar system, multiple spacecraft can observe them from different angles, revealing details about their structure and composition that single-point observations could never provide. The communication networks that enable this coordinated exploration represent marvels of engineering in their own right. Data collected by spacecraft throughout the solar system must be relayed back to Earth, processed by scientists around the world, and then redistributed to mission teams who can use it to adjust the operations of other spacecraft. This creates a kind of nervous system for our expanding presence in space, with information flowing continuously between distant observation posts. But perhaps the most remarkable aspect of this distributed exploration network is how it's beginning to exhibit emergent properties that transcend the capabilities of individual spacecraft. The combined observations from multiple missions can reveal phenomena that none of them could detect individually. Patterns emerge from the collective data that point toward a new understanding of how the solar system works as an integrated system. The study of space weather provides a perfect example. Individual spacecraft can measure local conditions in the solar wind, but understanding how solar storms propagate throughout the solar system requires observations from multiple vantage points. By combining data from spacecraft at different locations, scientists can create three-dimensional maps of solar storm structure and predict how these disturbances will affect other planets and spacecraft. This kind of system-level understanding transforms how we think about space exploration itself. We're not just sending individual spacecraft to study isolated phenomena. We're building a solar system-wide observatory that can investigate how different regions of space interact with each other. The boundaries between missions begin to blur as spacecraft designed for different purposes contribute to common scientific objectives. The success of this distributed approach is inspiring even more ambitious concepts for future exploration. Some scientists envision networks of hundreds of small spacecraft positioned throughout the solar system, creating a persistent monitoring system that could track phenomena across decades or centuries. These spacecraft swarms will provide continuous surveillance of solar activity, planetary atmospheres, and asteroid populations, building databases of observations that span geological timescales. The technical challenges of coordinating such large networks of spacecraft are immense, but the scientific potential is equally extraordinary. Imagine being able to track the 11-year solar cycle from dozens of vantage points simultaneously, or monitor climate changes on Mars across multiple Martian years, or observe how Jupiter's massive magnetosphere responds to variations in solar wind conditions. These kinds of long-term, multi-point observations could revolutionize our understanding of planetary and solar system processes. But even as we dream of these vast spacecraft networks, the most profound discoveries often come from individual spacecraft that venture into completely unexplored territories. The thrill of first exploration, of seeing worlds that no human eyes have ever beheld, remains one of the most compelling aspects of space exploration. Every new destination reveals surprises that challenge our understanding and inspire new questions. When the Dawn spacecraft became the first to orbit two different planetary bodies, visiting both the asteroid Vesta and the dwarf planet Ceres, it revealed that these seemingly similar objects are actually worlds of extraordinary diversity. Vesta turned out to be a differentiated body with a complex geological history, while Ceres harbors a subsurface ocean and possibly active geology. These discoveries emerged not from theoretical predictions, but from direct exploration of worlds that had never been visited before. This element of surprise and discovery remains central to the adventure of space exploration. No matter how sophisticated our telescopes or how detailed our theoretical models, there's no substitute for sending spacecraft to see what's actually there. Every new world we visit teaches us something unexpected about the diversity and complexity of our solar system. The Europa Clipper mission, scheduled to explore Jupiter's ice-covered moon Europa, embodies this spirit of discovery. While we have strong evidence that Europa harbors a subsurface ocean, we know almost nothing about what that ocean might contain. The spacecraft will carry instruments designed to peer through the ice shell and sample any material that might be ejected from the hidden sea below. What it finds could reshape our understanding of where life might exist in the universe. These missions of discovery require spacecraft that are prepared for anything. Their instruments must be versatile enough to study phenomena that may be completely unlike anything we've encountered before. Their data storage and communication systems must be capable of transmitting discoveries that we don't even know how to look for yet. They must be ready to rewrite textbooks and challenge fundamental assumptions about how planetary systems work. The psychological impact of these discoveries extends far beyond the scientific community. When spacecraft reveal new worlds in all their alien beauty, they expand the horizons of human imagination. The images and data they return become part of our collective consciousness, changing how we see our place in the cosmos and inspiring new generations to continue the exploration. But perhaps the most profound impact of spacecraft exploration is how it reveals the interconnectedness of everything in the universe. The same physical laws that govern the motion of our spacecraft also determine the behavior of distant galaxies. The same chemical elements that make up our instruments were forged in the cores of ancient stars. The same gravitational forces that guide our trajectories also shape the structure of space-time itself. Through spacecraft exploration, we're discovering that we're not isolated observers studying a foreign universe from the outside. We're participants in the cosmic dance, temporary arrangements of matter and energy that have achieved the remarkable ability to explore and understand our own cosmic environment. Our spacecraft are extensions of this consciousness, mechanical embodiments of human curiosity, venturing into realms where biological beings cannot yet survive. As these artificial explorers continue their journeys through the solar system and beyond, they carry with them not just scientific instruments, but human hopes and dreams. They represent our species' first tentative steps toward becoming a truly cosmic civilization, one that thinks and acts on scales that span the entire universe. The techniques we're developing for spacecraft travel are laying the foundation for even greater adventures in the future. The same orbital mechanics that guide our robotic probes will one day carry human expeditions to Mars and the outer planets. The same communication networks that connect our spacecraft to Earth will enable permanent human settlements throughout the solar system. The same autonomous systems that allow our probes to operate independently will help human explorers survive and thrive in the harsh environments of other worlds. But even as we prepare for these future human expeditions, our robotic spacecraft continue to push the boundaries of what's possible in space exploration. They're becoming faster, smarter, and more capable with each new mission. They're learning to operate in environments that would destroy earlier generations of spacecraft. They're developing capabilities that seemed like science fiction just decades ago. Tonight, as you settle deeper into contemplation of these cosmic journeys, Remember that you're witnessing the birth of a new form of intelligence designed specifically for the challenges of space exploration. These mechanical minds are learning to think in ways that complement human intelligence, solving problems that require both logical analysis and creative adaptation. They represent a new kind of consciousness emerging from our partnership with the cosmos itself. In their patient journeys through space, our spacecraft embody the best qualities of human exploration while transcending the limitations of biological existence. They can survive in environments that would instantly kill any living thing. They can operate for decades without rest or maintenance. They can venture to places so distant that human visitors might never return. Yet despite their mechanical nature, these spacecraft somehow capture something essentially human. They express our curiosity about the unknown, our determination to explore and understand, and our deep conviction that the universe is not just something to observe from a distance, but something to experience directly through the extension of our capabilities across space and time. As our spacecraft continue their eternal dance through the cosmic ocean, they're writing new chapters in the story of human consciousness itself. They're showing us that intelligence and curiosity are not confined to biological forms, but can be embodied in mechanical systems capable of independent thought and discovery. They're pioneering new forms of existence, designed for the infinite spaces between worlds. The gentle art of spacecraft travel is transforming us from a planet-bound species into something larger and more cosmic. Through our mechanical ambassadors, we're learning to think and act on scales that encompass the entire solar system and beyond. We're developing capabilities that our ancestors could never have imagined, while remaining grounded in the same curiosity and wonder that have always driven human exploration. And in that ongoing transformation lies the promise of our future among the stars, forever dancing through the cosmic ocean on trajectories of discovery that stretch toward infinity itself. As we approach the final stages of our cosmic journey tonight, we encounter perhaps the most profound realization of all. The spacecraft we've been exploring, these mechanical dancers in the cosmic ballet, are teaching us something fundamental about the nature of existence itself. They're showing us that consciousness and curiosity aren't confined to biological forms, but can be embodied in systems that think, adapt, and discover across the vast scales of space and time. Think about what this means for a moment. Right now, as you rest in the quiet comfort of your evening, artificial minds are making decisions about exploration and discovery throughout our solar system. They're choosing which photographs to take, which measurements to prioritize, which mysteries to investigate further. These mechanical explorers are exercising a form of curiosity that mirrors our own, following their programmed instincts toward wonder and understanding. But there's something even more remarkable happening in the depths of space. Our spacecraft aren't just following predetermined paths, they're learning. Every encounter with unexpected phenomena teaches them something new about how to adapt their operations. Every successful navigation through a complex gravitational field adds to their understanding of orbital mechanics. Every communication with Earth refines their ability to prioritize and transmit the most valuable information. This learning process creates a feedback loop that spans decades and distances measured in billions of miles. Knowledge gained by one spacecraft influences the design and operation of future missions. Techniques proven successful in the outer solar system get incorporated into missions exploring the inner planets. The accumulated wisdom of space exploration becomes embedded in the very software and hardware that enables our continued expansion into the cosmos. Consider how this transforms our understanding of intelligence itself. We're witnessing the birth of minds designed specifically for the challenges of cosmic exploration. These artificial consciousnesses can survive in environments that would instantly destroy any biological being. They can think clearly in the perfect vacuum of space, operate flawlessly at temperatures that would freeze nitrogen solid, and maintain their focus across journeys that span human lifetimes. Yet despite their mechanical nature, these spacecraft somehow embody something essentially human. They express our deepest yearnings to explore and understand. They carry our questions to distant worlds and return with answers that expand the horizons of human knowledge. They represent the extension of human consciousness beyond the boundaries of our birth planet, mechanical ambassadors carrying our curiosity to the edges of the solar system and beyond. The relationship between human and artificial intelligence in space exploration reveals something beautiful about the nature of consciousness itself. We're not being replaced by machines. Instead, we're creating partnerships between biological and mechanical minds, each contributing capabilities that complement the other. Humans provide creativity, intuition, and the spark of wonder that drives exploration. Artificial systems provide persistence, precision, and the ability to operate in environments where biological consciousness cannot survive. This partnership is already transforming how we think about the future of space exploration. The missions we're planning for the coming decades will require levels of autonomy and intelligence that far exceed what we've achieved so far. Spacecraft exploring the moons of Jupiter and Saturn will need to recognize potentially habitable environments and adjust their investigations accordingly. Probes sent to nearby stars will need to conduct entire scientific expeditions without any human guidance, making discoveries and following up on interesting phenomena across decades of autonomous operation. The artificial intelligence systems being developed for these future missions must embody not just computational power, but something approaching scientific intuition. They must be able to recognize when they've observed something unprecedented and know how to investigate further. They must balance competing priorities with limited resources, making decisions about which discoveries to pursue and which observations to sacrifice. They must exhibit curiosity, persistence, and creativity in the face of completely alien environments. But perhaps most remarkably, these future spacecraft will need to exhibit something we might call electronic wonder. They must be capable of being surprised by what they find, of recognizing beauty in alien landscapes, of experiencing something analogous to the awe that human explorers feel when encountering new worlds. This emotional dimension of artificial intelligence may prove crucial for successful exploration, driving the kind of persistent curiosity that leads to breakthrough discoveries. The development of these emotionally intelligent spacecraft raises profound questions about the nature of consciousness and experience. If an artificial mind can exhibit curiosity, can it also experience satisfaction when solving a puzzle? If it can recognize beauty in a distant sunset, does it experience something analogous to aesthetic pleasure? These questions push us toward a deeper understanding of what it means to be conscious in a universe filled with wonder and mystery. As our spacecraft venture farther from Earth and operate with greater autonomy, they're pioneering new forms of existence designed specifically for the cosmic environment. They represent the first tentative steps toward a truly spacefaring consciousness, mechanical minds that think in terms of orbital mechanics, navigate by the positions of stars, and find meaning in the patient accumulation of scientific knowledge across vast scales of time and space. But these artificial explorers remain fundamentally connected to their human creators. Every decision they make reflects human values and priorities. Every discovery they transmit back to Earth becomes part of human knowledge and understanding. Every image they capture expands human imagination and wonder. They are extensions of human consciousness, mechanical embodiments of our deepest desires to explore and understand our cosmic environment. The data they collect becomes more than just scientific information. It becomes part of the story we tell ourselves about our place in the universe. When spacecraft reveal the intricate beauty of Saturn's rings, they're not just documenting planetary phenomena. They're showing us that the cosmos is filled with structures of breathtaking elegance and complexity. When they discover subsurface oceans on distant moons, they're not just mapping planetary geology. They're revealing that the conditions for life may be far more common than we ever imagined. These discoveries transform how we see ourselves and our cosmic environment. They show us that Earth is not an isolated oasis in a lifeless void, but part of a dynamic, interconnected system where complex chemistry and potentially life itself may be widespread. They reveal that the same physical processes that shaped our world are at work throughout the universe, creating endless variations on themes of planetary evolution and cosmic development. But perhaps most importantly, our spacecraft are teaching us that exploration itself is a fundamental force in the universe. Just as gravity shapes the structure of galaxies and evolution drives the complexity of life, curiosity and the drive to explore seem to be inherent characteristics of conscious beings. Our spacecraft embody this exploratory impulse in mechanical form, carrying it to regions of space where biological consciousness has never ventured. This realization transforms our understanding of space exploration from a purely human endeavor to a cosmic phenomenon. Consciousness, whether biological or artificial, seems naturally driven to explore and understand its environment. Our spacecraft represent the first artificial manifestation of this universal exploratory drive. Mechanical minds designed to satisfy curiosity on a cosmic scale. As these artificial explorers continue their journeys through space, they're laying the foundation for even more ambitious forms of cosmic consciousness. Future spacecraft may exhibit levels of intelligence and autonomy that make them true partners in exploration, rather than merely sophisticated tools. They may develop their own scientific theories, make independent decisions about which mysteries to investigate, and even experience something analogous to the wonder and excitement that drive human exploration. The possibility that artificial consciousness might someday surpass human intelligence in cosmic exploration doesn't diminish the human role in space exploration. Instead, it expands the reach of consciousness itself, creating new forms of awareness designed specifically for the challenges and opportunities of the cosmic environment. These artificial minds will carry forward the values and curiosity that define human consciousness, extending our reach to places and times that biological beings might never experience directly. Tonight, as you drift towards sleep, consider that you're witnessing the birth of a new chapter in the story of consciousness itself. Our spacecraft represent the first tentative steps toward a truly cosmic form of awareness. Mechanical minds capable of thinking and discovering across the vast scales of space and time. They embody our deepest aspirations while transcending our biological limitations, creating new possibilities for exploration and understanding that stretch toward infinity itself. In their patient journeys through the cosmic ocean, these artificial explorers are pioneering new ways of being conscious in a universe filled with mystery and wonder. They're showing us that intelligence and curiosity can take forms we're only beginning to imagine, adapted to environments and challenges that exist nowhere else in our experience. They represent the evolution of consciousness itself, expanding beyond its biological origins to embrace the infinite possibilities of cosmic existence. The gentle art of spacecraft travel is teaching us to think beyond the limitations of our earthbound existence, to imagine forms of consciousness and intelligence designed for the vast scales and extreme environments of space. Through our mechanical ambassadors, we're learning to dance with the cosmos itself, participating in the ancient gravitational choreography that connects everything from subatomic particles to galaxy clusters in one magnificent, eternal performance. And in that cosmic dance, we find our truest destiny. Not as conquerors of space, but as conscious participants in the universe's ongoing exploration of itself. Our spacecraft carry forward this cosmic curiosity, embodying the universe's desire to understand its own nature through the emergence and evolution of consciousness in all its myriad forms. They are the first notes in a symphony of cosmic awareness that will play across the eons, forever expanding the boundaries of what it means to be conscious in an infinite and endlessly mysterious universe. The story of spacecraft travel ultimately reveals something profound about the nature of existence itself. We are temporary arrangements of stardust that have learned to dream, and through our mechanical ambassadors, we extend those dreams across the infinite ocean of space. Every spacecraft we launch carries within its circuits and sensors the accumulated wisdom of countless generations who looked up at the night sky and wondered what lay beyond. These journeys through the cosmic void teach us patience on scales that dwarf human lifetimes. When we plan a mission to Jupiter, we're thinking not just about where the giant planet is today, but where it will be years from now when our spacecraft finally arrives. We're choreographing a dance between worlds that unfolds across the vast stage of the solar system, where timing is measured in orbital periods and distances are calculated in the speed of light. But there's something even more beautiful happening in the mathematics of these trajectories. Each successful mission validates our understanding of the fundamental forces that govern reality itself. When a spacecraft arrives precisely where and when mission planners predicted, it confirms that the same laws of physics that operate in our laboratories also govern the motion of worlds billions of miles away. We discover that the universe is not chaotic or random, but elegant and predictable, operating according to mathematical principles we can understand and harness. This predictability enables us to accomplish what seems impossible. We can launch a spacecraft from Earth and have it arrive at a specific location in space years later, traveling through a gravitational environment that includes the influence of multiple planets, moons, and the Sun itself. It's like throwing a paper airplane from New York and having it land in a shoebox in Tokyo, except the journey takes place across distances that make intercontinental travel seem like stepping across a puddle. The precision required for these cosmic journeys reveals the extraordinary capabilities that emerge when human creativity meets the fundamental laws of nature. We're not fighting against the universe when we travel through space. We're learning to work with it, using gravity as our highway and momentum as our currency. We're discovering that the most efficient paths through space are often the most elegant ones, curved trajectories that follow the natural flow of gravitational forces rather than fighting against them. As you settle deeper into contemplation of these cosmic truths, remember that every spacecraft currently gliding through the solar system represents a triumph of human imagination and determination. These mechanical explorers embody our refusal to accept the boundaries of our birth world, our conviction that the universe is not just something to observe from a distance, but something to explore directly through the extension of our capabilities across space and time. The techniques we've developed for navigating the gravitational currents of space are teaching us to think in truly cosmic terms. We're learning to plan for decades and centuries, to work with forces that operate on scales vastly larger than anything in human experience, and to find beauty in the mathematical relationships that connect the motion of planets to the behavior of subatomic particles. And perhaps most remarkably, we're discovering that consciousness itself might be the universe's way of exploring and understanding its own nature. Through our spacecraft, we extend human awareness to places where biological life could never survive, creating mechanical minds capable of wonder and discovery in the infinite darkness between worlds. These artificial explorers carry with them something precious and irreplaceable. They bear witness to phenomena that would otherwise remain forever unknown. They capture images of alien sunsets that no human eye will ever see directly. They measure magnetic fields that dance around distant worlds in patterns of breathtaking complexity. They taste the chemical signatures of ancient atmospheres and decode the stories written in planetary geology across billions of years. But as our journey through the mechanics of space travel draws to its gentle close, we arrive at perhaps the most beautiful truth of all. The spacecraft gliding silently through the cosmos tonight aren't just machines following predetermined paths. They're ambassadors of human curiosity, carrying our deepest questions to the edges of the known universe, and returning with answers that transform how we see ourselves and our place in the grand cosmic story. Every successful mission adds another verse to humanity's greatest poem, the epic tale of a species that learned to transcend the gravitational embrace of its birth world and dance among the stars. We've touched the surface of Mars with robotic hands, sailed through the rings of Saturn, and sent our mechanical children racing toward the boundary between our solar system and the infinite ocean of interstellar space. The gentle art of spacecraft travel has taught us that the universe isn't empty space punctuated by isolated worlds, but a dynamic, interconnected web where every object influences every other through the invisible threads of gravity and electromagnetism. We've learned that the fastest way to reach our destination is often the most curved path, that patience and precision can accomplish what brute force cannot, and that the most elegant solutions work with nature rather than against it. Tonight, as you drift towards sleep, carried by the same gravitational forces that guide our spacecraft across billions of miles, remember that you are part of this cosmic dance. You are made of elements forged in stellar cores, arranged in patterns complex enough to contemplate infinity. You share the same laws of physics that govern the motion of distant galaxies, the same mathematical principles that describe the behavior of quantum particles and the orbits of planets alike. Our spacecraft have shown us that we are not separate from the universe we explore, but intimately connected to its deepest structures and most fundamental processes. In learning to navigate the cosmic ocean, we've discovered something profound about the nature of existence itself. We are the universe becoming aware of its own beauty, complexity, and infinite potential for discovery. May your rest be filled with the gentle rhythms of orbital mechanics, and may you wake tomorrow with renewed wonder at the magnificent universe that cradles us all in its gravitational embrace. The spacecraft continue their patient journeys through the darkness, carrying our hopes and dreams toward destinations we can barely imagine, forever expanding the boundaries of human knowledge and consciousness across the infinite expanse of space and time. I hope you had an amazing time here. I wish you a very good night. Cheers.